Hello, class. Welcome to week 4, where we're going to talk about the fundamental theorem of calculus. And then we'll do a bunch of examples of using it to calculate some integrals. So, first of all, I want to remind you where we are so far, which is that we have defined two kinds of integrals. We've defined, on the one hand, the indefinite integral, and on the other hand, the definite integral. Remember that the way we tell these things apart is whether there are numbers written on the axis. So it is these 0 and 1 that tell me that this on the right is a definite integral. And ostensibly, these two concepts don't have anything to do with each other, because this indefinite integral, it is an antiderivative. So the indefinite integral is a function whose derivative is x squared. So this is going to be x cubed over 3 plus c. And I want to remind you that indefinite integrals always come with this plus c factor here tacked on the end. Okay, so that is indefinite integrals. On the other hand, we have definite integrals, and these things have to do with area. Okay, and to be very precise, they have to do with signed area, by which I mean that we count some area as positive, namely the area that's above the x-axis, and some area as negative, namely the area that is below the x-axis. And so if you were to ask, what is it that this thing represents? Well, if you drew your graph of x squared, and you went over here to 1, 1 on that graph, then this is that area. This area. That is the area between 0 and 1 under the graph of y equals x squared. So this is this little almost but not quite triangular shaped region, right? It's not technically a triangle because this is a parabola, so that side is curved. Okay. Now, notably, we know how to calculate the indefinite integral in this case. In fact, I did it already. But we don't know how to calculate this, right? We probably did not get any geometry formulas in your geometry class that told you how to calculate areas under parabolas or in parabolas or anything of that sort. So we want to make sure we go back and carefully piece together how we'll do that later. But at this point, it should really bother you that we called both of these things integrals, but the two have absolutely nothing to do with each other as far as we've seen so far. Namely, this antiderivative is some sort of function with a plus c, whereas this is some number. I don't even know what number. And so I want to figure out how the two are related. And so this week is all about that relation. And so that relation is via something called the fundamental theorem of calculus. I guess I didn't really have to rewrite that. But I did, so it's too late now. And what does the fundamental theorem of calculus say? It says that if little f of x is a function continuous on AB, and f of x, big F of x, is an antiderivative of little f of x, then the integral from a to b of little f of x is given by the formula big F of b minus big F of a. So in effect, what this is saying is that the antiderivative, big F of little f, it encodes all of the information about the area in such a way that you can recover the area under the curve just by plugging in 2 points, namely the 2 endpoints, and subtracting them. So even though it's not framed that way, the antiderivative function is really encoding information specifically about area. And so, if you believe this fundamental theorem of calculus that I just told you, we can go ahead and calculate this integral from 0 to 1 of x squared. Namely, let's go ahead and do that. What is this integral going to be? Well, first of all, my little f here is the function x squared. That's the function that I'm integrating. It's that piece. So my big F is an antiderivative here. I'm going to choose x cubed over 3. Note, I'm usually just going to take the c to be 0. You could take the c to be something else if you wanted, but I just need an antiderivative, so I don't need the most general antiderivative. But anyway, that's what we got when we calculated the indefinite integral over here. A is 0, b is 1. And so the integral from 0 to 1 of x squared dx is big F of 1 minus big F of 0, which is 1/3 minus 0, which is 1/3. So our conclusion is that the area under this one particular bit of the parabola, y equals x squared, is exactly 1/3. Okay, we're going to do a whole bunch more examples of applying the fundamental theorem of calculus in the next video. But that gives you just the idea of what this is and the kind of question it allows us to answer. Namely, what this is going to let us do is it's going to let us calculate a lot more definite integrals than we were able to before. And namely, we're going to be able to calculate any definite integrals of functions that we know antiderivatives for. Okay, I'm going to stop there for this video. Until next time, be well.